Okay, let's dive into one of the absolute classic computer science puzzles. You see this thing everywhere, from coding interviews to real-world problems, and today we're going to break it down. So first things first, what problem are we actually trying to solve here? Because you'll see, it comes in a couple of really important flavors. Let's start with a question you've probably answered 1,000 times without even thinking about it. You're at a store, you need to make 41 cents. What do? Well, you'd probably grab a quarter, then a dime, a nickel, and finally a penny. Simple, right? But how our brains do that so automatically? Well, that's the interesting part we're going to unpack.
So, that one simple question actually splits into two different challenges. The first is what we just did. It's an optimization problem. How do you find the minimum number of coins? But the second variant is all about counting. How many different combinations of coins could you possibly use to get to that same amount? We're going to tackle both, but let's start with finding that single best solution.
All right, so let's talk about the most obvious, most intuitive way to solve this. And then we're going to see how that gut instinct can lead us straight into a trap.
So this intuitive method has a name. It's called the greedy approach. All it means is that at every single step, you just take the biggest coin you can without going over. You need to make 41 cents? You grab the 25-cent piece first. It feels right, doesn't it?
Now, you might be thinking, hey, this always works for me. And you're right, for the money in your pocket. That's because our real-world coins were basically designed to make this greedy method work. But what happens if we're in a weird universe with a different set of coins? Let's say our only coins are worth 1, 3, and 4, and we need to make an amount of 6.
And boom, here's where it all falls apart. If we're being greedy, we see the amount is 6. The biggest coin we can grab is the 4. Great, now we have 2 left. The biggest coin that fits is a 1. Okay, grab that. Now we have 1 left. Grab another 1. That gives us a total of 3 coins, a 4, a 1, and another 1. But, hang on, look at the optimal solution. What if we had just taken 2 3s? 2 coins is obviously better than 3. Our simple, intuitive, greedy method completely failed us.
So, if our gut instinct can't be trusted, what's the foolproof method? Well, that's where a really powerful technique called dynamic programming comes in. What's the big idea with dynamic programming, or DP? It's actually pretty simple. Instead of jumping ahead and grabbing the biggest coin, you patiently build your way up from the bottom. You figure out the absolute best way to make 1, then the best way to make 2, then 3, and so on, using the answers you've already found to solve the next bigger problem.
I love this way of thinking about it. Imagine a number line, from 0 all the way to your target amount. To figure out the best way to get to, say, position 6, you don't have to guess. You just look backwards at the spots you've already solved. You can ask, hey, what was the best answer for 5? I can just add a 1 coin to that. Or, what was the answer for 3? I can add a 3 coin to that. You check all your options based on the coins you have, and you just pick the one that gives you the smallest total.
Okay, let's actually build one of these DP tables together. Let's say we want to make 5 using coins of 1, 2, and 5. We start at the beginning. The answer for 0 is, well, 0 coins. That's our base case. To make 1, it takes 1 1 coin. To make 2, it's just 1 2 coin, which is better than 2 1s. To make 3, we look back. We can add a 1 coin to our solution for 2, giving us 2 coins total. See how that works? We just keep building, and by the time we get to 5, we know that the absolute best way is to just use that single 5 coin. No guesswork. We've proven it mathematically from the ground up. Okay, so we've totally nailed down finding the minimum number of coins. Now, let's switch gears and tackle that other big question. How do you count all the possible ways? And this is where we hit a really crucial question. Are we counting combinations or permutations? In other words, does the order of the coins matter? Is using a 1 and then a 2 the same as using a 2 and then a 1? If order doesn't matter, we're talking combinations. If it does, we're talking permutations. Now, what's really wild is that the answer you get depends entirely on how you structure your code. If you loop through your coins first, like consider all the ways using pennies, then add nickels to the mix, and so on, you'll get the unique combinations. But if you loop through the amounts first, you'll end up counting the same sets of coins in different orders, which gives you the permutations. A tiny change in code, a completely different answer. All right, let's bring it all home. Think of this next part as your cheat sheet for when you, inevitably, see this problem in a technical interview. So, why do we even bother with all this DP stuff? Well, this table tells the whole story. It's all about speed. A simple, naive, recursive solution that just tries everything, its runtime is exponential. That means for bigger amounts, it could literally take days to finish. But our dynamic programming approach? It's way, way more efficient. Its speed is just the number of coins times the target amount. We're talking the difference between a split second and, well, forever. This is how you solve it like a pro. So you're in the interview, and this question drops. Here's your playbook. First thing you do, clarify. Ask, are we looking for the minimum number of coins or are we counting the combinations? Then state your starting point, your base case, like the answer for amount 0 is 0. If you're counting, explain why your loop order is the right one for the job. And here's the pro move. Mention the greedy trap. Having that 1, 3, 4 example in your back pocket shows you've really thought about the edge cases. And finally, state the time and space complexity with confidence. You do these things, and you've absolutely crushed it. You know, the real magic here is that this isn't just about coins. This is a pattern. It's a way to solve any problem where you need to combine some set of fixed building blocks to hit a specific target. It could be cutting stock material with minimum waste, figuring out inventory, or anything like that. So I'll leave you with this question. Now that you see the pattern, what other real-world problems out there are just the coin change problem in disguise?